A capacitor has the capacity to hold an electrical charge. And when a capacitor is charged, it acts as a voltage source. A capacitor typically consists of two plates of metal, closely spaced, separated by air or a dielectric material. A typical ceramic capacitor is shown in the diagram with a ceramic dielectric between the plates. As electrons flow into one side of the capacitor, either side, they create a negative charge on that plate, which creates an electric field between the plates, which repels the electrons in the opposite plate, forcing these electrons to flow out of the capacitor. Thus, current appears to flow through the capacitor even though electrons don't pass between the plates. The voltage supplied by a charged capacitor equals the coulombs of excess electrons on one plate divided by the capacitance of the capacitor measured in farads. So if 1 amp of current flows into an initially uncharged 2 farad capacitor for 3 seconds, the capacitor will have 3 seconds times 1 coulomb per second excess electrons on one of the plates, and the voltage across the capacitor terminals will be 3/2 or 1.5 volts. Current I, that is I coulombs of electrons per second, flowing into or through a capacitor causes the excess electrons on one plate to increase at a rate of I coulombs per second. So the voltage increases at the rate V sub C prime of t equals I divided by C. This is true if current varies with time, so the differential equation model for a capacitor is V sub C prime of t equals I of t divided by C. Let's see what happens when the switch is closed in a simple circuit containing a capacitor. Assume that the initial charge on the capacitor is 0, so that when the switch closes, the voltage across the capacitor terminals is 0, and so the entire battery voltage appears on the resistor terminals. Thus, at time t equals 0, the resistor voltage is 1.5 volts, and by Ohm's law, current flows through the resistor at a rate of 1.5 volts divided by 5 ohms, or 0.3 amps. So current starts flowing the instant the switch is closed. Current charges the capacitor, and the resulting capacitor voltage opposes the battery voltage. As the capacitor voltage increases, the current decreases. At time t, the voltage on the resistor is the battery voltage, 1.5 volts, minus the capacitor voltage, V sub C of t. And the current through the resistor is 1.5 volts minus V sub C of t divided by 5. The capacitor continues to charge, and the current continues to decrease until the capacitor voltage equals the battery voltage, and then the current stops. We need one law to begin a quantitative analysis of the circuit, and that is Kirchhoffs Voltage Law, which states that the voltages across the components in a circuit loop sum to 0. If the polarities of all the circuit components are oriented in the same direction, as in the circuit diagram on the slide, then Kirchhoffs voltage law is written as a sum of the component voltages as follows: V sub B plus V sub C of t plus V sub R of t equals 0. But note that while the battery polarity is physically determined, we get to, that is, we must, choose the polarities of the resistors and the capacitors. And we have to take the polarities into account when using Kirchhoffs voltage law. So if we chose the polarities differently, as shown in the next slide, we have to adjust the signs in Kirchhoffs voltage law, and it is written as shown, taking into account that the capacitor and resistor polarities are aligned opposite the battery polarity. Polarities are assigned with the goal of making the final circuit model more readable. The state of the circuit is the state of each component capable of storing energy in the circuit. that is, for each capacitor and inductor in the circuit. Our circuit has one capacitor and no inductors, and the state of the capacitor is its voltage. So the circuit model will have one state variable, the capacitor voltage V sub C, and we need a differential equation for its rate of change. So what do we have to start with? We have the capacitor model, we have the resistor model, and we have Kirchhoffs Voltage Law. And from Kirchhoffs Voltage Law, we can derive that the resistor voltage equals the battery voltage minus the capacitor voltage. So, starting with the capacitor model, we have V sub C prime of t equals I of t over C, and I of t equals V sub R of t divided by R, so we can replace that in the equation. And V sub R of t equals V sub B minus V sub C of t, so we make that substitution, and we have the differential equation model for the circuit. That is, V sub C prime of t equals V sub B minus V sub C of t divided by R divided by C. So we follow our usual procedure and translate the model into a computational equation, and then we'll write a MATLAB program to perform the necessary calculations. It's sometimes a good idea to do a few calculations by hand and to compare the values to the first few values computed by the program. So a few values are calculated by hand on the slide. Program results for the parameters given on the previous slide are shown. The initial capacitor voltage is 0 and increases to 1.5 where it levels off, and the initial current is 0.3 amps and it decreases to 0. So that's what we'd expect. The assignment is to program and run the capacitor circuit model with the parameters given in the video, and also run it with a battery voltage of 0 volts and an initial voltage on the capacitor of 10 volts. First, predict what will happen, then run the program and see if you were right.